M&Ms. No, these are for me. Hey, guys. Hey, I bought these for me. I'll share some. You guys sit down, you can make a little box and I'll fill your box up. Just cut the corners out of that paper and you can build a box and I'll fill it up. The rest are for me.
I'll take mine.
You'll take yours?
Okay, so that video kind of raises the question of, does it matter how big the corners were that they cut out? Did they all have the same number of M&Ms? Does the volume stay the same regardless? Well, Carson was pretty excited to have his box of M&Ms because it actually had more than what the other two boys had. So if you were in class, you got to follow up with that. But so that was kind of how we started this, looking at the volume of a box that doesn't have a lid. That's why we call it an open-topped box. And we're looking at really maximizing it. What would have been the best bet for those guys what size squares should have they cut out to maximize the volume so they got the most M&Ms? Okay, so that's what we're looking at today. Now, the other thing that we did in class is we went ahead and took a piece of paper, just a regular piece of copy paper, and everybody cut out corners. Now, we kind of gave everybody different sizes, so we had some nice variety on these. And so everybody had to create this box. They cut the corners out, and once those corners are cut out, then they can kind of just fold along here, and these all be kind of flaps and the sides of the box, and then they tape it together. Now, let's just pretend that you were given the size of, okay, and let's do this in centimeters. And in centimeters, these sides are 21.5. And the long side is a 28, and that's measured in centimeters. So let's say that we gave you a 2 centimeter size square to cut out of the corners. All right, so what we did then is compared all the boxes as they were built to see if they had the same volume or if we thought one was larger than the other. And when you get a nice sampling of sizes, it was pretty obvious to tell then they're not all going to have the same volume. So what we did then was to come up with, confirm our answer from above by finding, everybody had to go find their volume. So let's work on yours. Okay, so the volume of a box is length times width times height. Okay, so for your volume, your length, well, the length of the paper is 28, but once you cut those corners out, the length really is only this long, because then it gets folded up, right? And so the base of the box is really this blue box here. Okay, so then that length is actually the 28 minus the 2 centimeters, so minus 4 centimeters. So the length was really 24 once that box got built. Okay, now the width used to be 21.5 centimeters, but we cut 2 centimeters out here and 2 centimeters out here, so it's really 21.5 minus 4. Okay, so that would give us, for a width, 17.5 times the height. Okay, the height of the box is how tall those flaps actually were once they folded up. So this right here would have been the height of that box. Well, since our square was 2 centimeters, then our height is 2. Okay, so then if I go to my calculator, so 24 times 17.5 times 2 would give you a volume of 840 cubic centimeters. And then as we started comparing everybody's, we could see the variation in those volumes. All right, so what we want to be able to do is figure this out without everybody having to build a box and then compare them and sit there and do trial after trial. So what we're going to do is we're going to do this again, and we're just trying to come up with a volume. Now, the only measurements we really knew were the size of the square. That's it. And I take that back. We knew that. We also knew the size of the square that we cut out. We called that X. But we actually had, because that varied for different people. But for yours, we knew it. But since it changed, we're going to call it X. And then we're going to use that size of paper because everybody had the same size of paper. So if you think about this, let me kind of redraw this. Here was our piece of paper. Now it started out 28 centimeters. But then you had to cut out a square on this side, and we said that that was X by X. But you also had to cut it out on this side, okay? And so what was the length of the box, which really ended up being this measurement from here to here? How long would that be? Well, it was 28, remember? And then you have to subtract out the 2 squares. Now, your example, they were 2, but that wouldn't have worked for everybody. In our picture now, that measurement is X. So you'd have 28, but you didn't just subtract it from one side, you subtracted it from both sides. So the length is now 28 minus 2X. Okay, can you figure out what the width should be then for our volume function? Hopefully you're thinking 21.5 minus 2x, because you have this right here. This was the 21.5, but this is the new width once you fold up all the sides. So it's the 21.5 minus the x measurement on both of those. Okay, and then the last thing is the height. Okay, the height is how tall the flaps are, because that's how you build up the height as you fold it up. Well, the height of the flap is just x. So this becomes the volume function. In fact, this is always the volume function. The only thing that would ever change to find the volume of an open box like this is if you had a different size piece of paper. And my boys, when they were doing the M&Ms thing, they didn't have the full-size piece of paper. That would not have left me near enough M&Ms for myself. So I gave them a little sheet of paper. Okay, so these numbers can change, but you'll always be subtracting twice or 2 of those squares, so 2x on both of those. And your height will always be that x measurement, however big of a square you cut. Okay, so what we want to do then is go to our graphing calculator and graph this volume function we came up with. Okay, so you're going to need this in your calculator. Go ahead and pause the video and type that into your y equals. Now, the other thing that you're going to want to do there is fix your window. So you'll have to play with your window a little bit until you can get a good view of that, the graph. Okay, so let me help you a little bit with your window in case that isn't working out for you. You kind of have to use some common sense as you're trying. I mean, you can sit there and just zoom out a couple times and you're going to kind of get it, but you want to be able to see what that graph really looks like in an appropriate window. Let's talk about our X window first of all. Look at your picture and look at what X represents. Would it make any sense for that X to be negative? Not really. So I usually let it go negative a little bit just for a little buffer. But I'd probably go from -5 and then think of how big that X, how big of a square are people going to be cutting? You know, I don't know. We could go maybe to 20 or so. I don't know. So let's put in something like -5 to 20. That's what I'm going to go with. I haven't done it yet, so I'm going to do it as we go. Okay. And I'll probably just leave my scale at 1 for now. Okay. And we're going to kind of tweak this window a little bit later. So right now I just want to get a decent picture of this wave. I already know, okay, so from our graphing packet, that's why this kind of comes into play in this area, is because from our graphing packet that we have done, we can tell that we have an X times an X times an X. So this is a cubic, and they're all to the first power. It should start low, come up, do a wave, and end high. We know what a cubic should look like. So I'm trying to get a graph that actually looks like that. If I look at my y's, my y is basically the volume. Okay, so let's look at what would be a reasonable volume. First of all, are we going to have a negative volume? No, that doesn't make sense. So it won't be negative, but we got to think about how high it needs to get. So just look, it's just length times width times height. So just look, I mean, this is about a 30. This is about a 20. So 30 times 20 is 600. And I don't know, let's say that this was maybe, you know, it really could vary for everybody, couldn't it? So if it was 10, maybe, was that reasonable just to throw a number in there? So let's go with maybe a 3,000. Okay, so here's what I'm going to do. I'm going to let my y min be -3,000, which doesn't make any sense at all because I'm not going to have a negative volume, but I just want it to look a little bit symmetrical for right now. And I'm going to let my y max be 3,000. And I'm hoping that your calculator's in front of you and you're kind of doing this with me, or maybe you already have a nice graph. But when I graph something like, okay, oh, that's nice. Oh, that's beautiful. That's gorgeous. Okay, here we go. So I'm going with that window. That was a good one. So I went from -5 to 20 on my x-axis, and I went -3,000 to 3,000 on my y-axis, and I got a graph that looked like this. And it was a nice cubic graph. Okay, so get your graph to look like that, because then we're going to do something with that. All right, so it says, use the key parts of this graph to help you discuss the real-life meaning of this function. Okay, so we have worked a lot with just some generic equations. This whole packet has been full of beautiful polynomial functions that have no meaning to us. So this one actually has some meaning of what's going on with it. So when you have this graph that looks like this, let's talk about what's going on with this graph. It's important for you to understand what your x-axis is representing. Remember that the x in this is the size of square that got cut out. So think of all of the x values as the size of that square. You can't really read that, but. And then the y in this is your volume. So think of all of the y values as your volume. That's your axis on the y-axis. Okay, so it says state the domain and the range of your function. So when I look at this, if I graph it nice, it's easy for me to see that this graph is going to go forever left and forever right. And it also happens to go forever down and forever up, so my range is also negative infinity to infinity. However, that isn't true in a real life situation. Look at what our x represents. Remember, that was the size of square that we cut out. So let's draw that picture again. That told me how big of a square that I was cutting out. And if you think about this for a second, let's go with this 28 that we had here. Now, as that square gets bigger and bigger, so the next person had a bigger square they had to cut out, but they had to do it on both sides. And the next person had an even bigger square. Okay, at some point, these two sides, they're going to touch. And basically, I'm going to cut my paper in half, and I'm not going to have a box anymore. So what would be the limit to how big of a square you could cut here? Well, it's really till you get halfway in there. When you get halfway, all of a sudden you've cut your paper in half. So 14 would be your halfway point. Okay, except that I picked the long side. That doesn't really work. I can't do that. What I really need to do is look at the short side of this, because that's 21.5. And this same thing is going on this direction, right? And so as those get bigger and bigger, at some point I'm going to hit the middle of that. So it's really halfway on my smaller side. So 21.5 or 21.5, take half of that, you're going to be at 10.75. So really that's the biggest size square, and even that would be too big because at that point they'd be touching. So consider what your x represents. That's the size of square that I'm cutting. So what's the real life domain? Okay, well the smallest, well, it would be 0. Can't go negative. I can't cut a negative square, but the most it could be is 10.75. And that's always going to be half of your shortest side. That's what the domain will end up being. Now, I'm going to put parentheses on these because I can't really let them be those measurements, because if it's 0, I don't even have a box. It's just a flat piece of paper. And at 10.75, my two squares have met, and I'm going to have a flat piece of paper. So my real life domain should be 0 to 10.75. So it says adjust your window to reflect this. So as promised, I'm actually going to go tweak this again. So on my x min, I'm going to go 0. My x max, I'm going to put 10.75. Okay, let's try it again with our range. Okay, so the y is actually the volume. That's your v equals, or in this case, your y equals. So let's think about what the min and max volume would be. All right. Well, we kind of talked about it. We really oh, I guess it says here, I should follow your sheet. I get ahead of myself here. With your adjusted domain, what is your real life range? Okay, so let's go back and look at that graph again. Once we've cut it off to what that domain is, all of a sudden, the only thing you see on your graph is this spot where it goes from 0 to where it comes back and touches. So my graph looks kind of like this now, and this is all I see on it, is where it crossed at 0, and so my window is kind of like this right here right now. That's what I see. Okay, so what's the real life range when you're only using a chunk of that graph? Well, now the lowest it ever goes is 0. And the highest it ever goes is this spot right here. Okay, can we find that maximum spot right there? Well, we've done that. Let's find the maximum. So on your calculator, you're going to go second calc. And number 4 is your maximum. And then you got to go left, 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 left until you are plenty left of that maximum. And then you go right, 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 right until you are plenty to the right of that maximum. I actually have kind of a big flat line there, so make sure you get far enough on either side. You can make a guess. I usually just press enter there. And let's look at what we got. Okay, so here's what I have. This point right here at the peak right there. That ordered pair for me is 4.02 and 1080.02. Okay, so when I look at what my real life range is, what's the highest this graph ever gets? Well, the highest it gets is this y value. So then my real life range is 0 to 1080. And again, because they couldn't actually be those measurements, I'm going to leave this with parentheses on it. Okay, and then the last thing, what other value would be of interest on your graph? Find it and discuss what it means in terms of the real life problem. Well, actually, that's the ultimate goal. This was what we were shooting for the whole time, is what's the main feature on this graph that I want? Well, it's that maximum I just found. That's what I want to know, because that is the highest my graph ever gets. Remember that that's the y value. That's the highest volume. That would get me the most M&Ms if I could maximize my volume at that amount. Now think about what this means for that. Okay, this was the size of square you cut out. Okay, so if I cut this size square, I could maximize my volume here. Okay, that's ultimately what we're looking for, is that maximum right there. So let's write a nice sentence that says that. All right, so basically, and I'm going to want a nice sentence from you on this. I'm going to say something like, you will maximize the volume at 1080.02 centimeters cubed when you cut, and I am out of room down here on the bottom. It doesn't let me get any lower. So when you cut a 4.02 centimeter square out of the corners or something like that. I'm out of space. I'm going to call it quits on that sentence. But make sure that you express both the x value and the y value, and express what they mean in this problem, and be sure that you use labels. And that's the holy grail right there of what we were looking for. All right. Have fun with that. Anticipate this problem coming up numerous times throughout the semester. You really need to understand how to write that function, and then how to find the key parts of your graph. All right, good luck.